Here, this building that we are in right now was built something like 70 years ago. And the purpose was to host a telescope, which you will be visiting later today. And this telescope has been used mainly for educational purposes, but also recently for research purposes. For example, to observe the passage of asteroids in the solar system. It has been verified as such research telescopes very recently. So today, the program is that we will have a remote connection with another research group in Crete who are operating a large telescope on a mountain in Crete. So you will be doing this remote interactive session with them. And after this is over, you will be able to come up to our telescope and hopefully we will be able to see some nice things in the sky. For example, Saturn. All right. So I wish you a successful night today, but before that, I would like to ask Professor Sakellariadou, who is also here today, to maybe express your impressions so far of this school.
Thank you. So good evening, everyone. It's actually a great pleasure to see so many kids, if I can say, to be interested in topics of astronomy, astrophysics, and all that. I mean, I think that this initiative is absolutely great for many purposes. I mean, on the one hand, it cultivates scientific curiosity, which is very important. On the other hand, I think nowadays even more than in the past, to have people from different countries to discuss, to exchange ideas, to exchange, I don't know, fears they have, hopes they have for the future. I think you should indeed take advantage. Being for a week with people with the same age, but from a different country, to realize that all of us were actually, very identical. And I think that this is a very good chance that you have, and not everybody has. Very different to go somewhere like a tourist and go somewhere to live with people with the same kind of leadership. So I hope that you really will enjoy this week. I'm pretty sure because from what I saw the program, you have a variety of topics that you can cover, not only from lectures themselves, but the labs. This is something very important because you can understand what is behind the theory of some kind of lecture somebody gives. And to have the chance to be able to see up there, it's really very, very nice. So I'm sure that you will enjoy the time, but nevertheless, I would like to wish you the best on behalf of the European Physical Society and on behalf of somebody who's in this field and come from this country. So enjoy your time and have fun.
Well, and I would also like to thank my colleague, Ioannis Golias, assistant professor here in our department, who was very kind to be here today and to assist with the operation of the telescope, and also two of our students who are experts in this. We will meet them later today. And now, Manolis Haniotakis will take over for this interactive session with Skinakas.
Okay, so welcome all from me as well. I will now connect you here. So I would like to introduce you to the team of the Skinakas Observatory. Panagiotis, Evangelopoulos. Panagioti, can you hear us?
Yeah, I can hear you.
Perfect. Let me connect. Okay. So without further ado, I give the floor to Panagiotis, who together with Dmitry and Kalliopi will be guiding us through the cosmos via the Skinakas Observatory. Panagiotis, the floor is yours.
So thank you very much for your invitation, Manolis and the other guys from Ελληνογερμανική Αγωγή, and also have to thank the venue of University of Thessaloniki, of course. I'll give you a really brief presentation of our activities according to the public outreach. And after this, we'll have the honor to have postdoctoral researchers of the Institute of Astrophysics right now at Skinakas Observatory, Dmitry Blinov, who will give us a presentation about his expertise in polarization and the polarimetry of RomboPol that is really a vital equipment of the Institute of Astrophysics and of course the University of Crete, according to the observatory of Skinakas. So, apart from, of course, scientific research and major research infrastructures, there is 20 plus years successful astrophysics activities in Crete. And the last 3 years, we have more consistent educational public outreach activities according to trainings of students and postdocs to address key outstanding problems, organizing stargazing events, and we have directly involved for influencing astronomy in STEM curricula with a major partner, which is Germanic, of course. As concerning these activities, of course, we have open nights at Skinakas Observatory. It's not so obvious that research infrastructure is open for a few nights for the general public. We have really narrow cooperation with amateur astronomers groups. And another fact that you didn't expect is that Psiloritis is a UNESCO World Geopark. So through the observatory, we can show this kind of geopark in Eastern Mediterranean. Of course, there are some cultural events with the municipality of Anoia and Heraklion. We have a really good collaboration because Anoia is really vital for the development of this observatory at the last 40 years, of course. At the last 4 years, we organized the annual School of Astrophysics of Crete, which is orientated to first and second class students of high school here in Crete. You'll see further information in a few slides. We support the high school teachers' hard work with a prize, Eureka Prize, and many more. For possible future university students like you, think about that we have also really high level of education, only, of course, in university, but also through Onassis lectures. You'll see further information in a few slides. So this is the top of Skinakas with 3 domes with the minor telescope with 30 centimeters diameter. The middle one with 1.3 meter diameter, in which actually right now Dmitry and Kalliopi are, and there is another dome at the right side in which there is a 60 centimeter diameter telescope, which is fully operated remotely by a German team of observers. And of course, there is infrastructures that support the stay of Dmitry and his team for as many days as he wants for the observations. This is the minor telescope, was installed at Skinakas in 1986. with a purpose of better education in astronomy for university students. This is the 60-centimeter telescope, and this is the big one. Dmitry will show you later. Sorry. So during open nights, we give the opportunity to every person who can be in 1,750 meters altimeter. We give the opportunity to observe through an eyepiece through the big telescope since 1995. Think about that, we have approximately 2,000 visitors per year. And the last few years, we have a support of university students with smaller portable telescopes. And also we have until sunset solar observation with solar telescope. This is not the end of what we'll have at the top of Skinakas. We will have a new building at the next year with support from Committee Greece 2021. This building will host another telescope, and we will have an amphitheater with 85 seat lecture hall. So we can improve all the conditions and for our visitors, and we make the opportunity to have seminars and lectures also at the top of Skinakas. Concerning the School of Astrophysics, this is a remote school with 8 lectures via the web, covering all topics of modern astrophysics. You are really quite familiar with the astrophysics even at your age. You could see that there are different fields of astrophysics, so we make this kind of introduction to interested students that are across Crete. And there are also some prizes for the top students, like 2 nights stay at the observatory and free astronomy books from Crete University Press. I told before about the support at the really hard work of really innovative teachers in Greece, and we have this kind of prize especially for teachers that are struggle with local community, that have really hard work to do. Our column to start the STEM education were 2 actual projects: DSpace, Discover Space, funded by Hellenic Foundation for Research and Innovation, and La Skill, funded by Erasmus+. And these 2 projects, we have a huge partner, which is Ελληνογερμανική Αγωγή, actually, and some other schools across country, and some honorable mentions like School Pankriton in Heraklion and School of European Education. Of course, there is our YouTube channel with many videos. You can scan this QR code. You can find also videos in English from our top researchers and professors here in Crete in many astrophysical issues. And of course, there is Facebook page. And I strictly recommend you to visit our photo gallery, gallery.ia.forth.gr, in which you can see many spectacular astronomical images only from the Skinakas Observatory. We are really active about the publications. I also recommend you to search for these new bestseller at the left side, The View to the Universe, which is in English, and it has many pictures, really gorgeous pictures of the observatory for astronomical targets, of course. And at this you can find really basic informations about the observational astronomy and how we take these pictures. And in university level, we are really proud of having approximately every year a Nobel Prize winner or a field medalist or Turing Award recipient as a key speaker for our NASA's lectures. And for the top university students, there is the opportunity to have these leading scientists to teach these students, not only in physics, but also in chemistry, biology, and computer science. Think about that. The theme of the lectures of last year was applications on extreme light. So this is by me. We want to improve all this kind of organization, of course. We expect to have a new 1-meter telescope in Skinakas maybe the next year, for the opportunity of remote observing and training to basic astronomy skill to all high schools in Greece. And of course, to have tour for schools and visitors at the new solar system scale model that we have at the next month in our facilities for events like Research at Night, etc. So as you can see, I believe, not only me, but all the researchers here in Crete, that there is also a bright future for astrophysics in Crete and in Greece generally. Thank you for paying attention to me. I'll give the talk to Dmitry right now. Dmitry, give me 1 second to say a few words about you. Okay.
Hello, everyone. Can you hear me?
Yeah, we can hear you. Let me tell a few words about you, and after this, the stage is yours. Okay. So, Dmitry Blinov is our presenter today. He's a postdoctoral researcher of the Institute of Astrophysics at the group of Professor Kostas Stasis. About his education, obtained his master degree and PhD in astronomy at the University of St. Petersburg in Russia in 2008 and 2011. About his career, after a short period of junior research fellow at the Astronomical Institute of St. Petersburg University, he moved to Crete in 2013. So many years, Dmitry, here. In Crete, he has been a member of the RoboBall project, an international collaboration of optopolarimetric studies of active galactic nuclei. His research was mainly focused on studies of optical polarization behavior in blazars and its connection to high energy emission of these sources. Since 2017, he has joined the Pacify project, an international collaboration on the mapping of polarized foregrounds of cosmic microwave background beam mode searches through a large-scale optopolarimetric survey of high galactic latitudes. And his research interests are optical polarimetry, of course, the active galactic nuclei, high-energy astrophysics, and the magnetic fields in the Milky Way and extragalactic environments. So thank you for your vital time, Dmitry. Your time is yours right now.
Okay, thank you, Panagiotis, for the introduction. So we are here together with Calliope. She's a student.
Hello,
Where are you from?
I'm from Crete, and I'm studying physics in University of Ioannina in Greece. So I'm postgraduate, and I'm doing my practice here in the Observatory of Skinakas for this summer. So yeah, that's it from me.
So today, together with Calliope, we will be observing mostly blazars in optical polarization. So we are actually now starting the observations here. There is the control room of a telescope. We will use like 3 computers at least for this. And I will show you the telescope itself. So it's located 2 floors up. So let me go there. Okay, here it's obviously dark because we are starting. I will put a bit more light. Okay, I hope you see now the telescope itself. You see the slit of the dome is open. So this is the largest telescope of the Skinakas Observatory for the moment. This is the main mirror. The diameter is 1.3 meters. This is the secondary mirror. And here we have 3 different instruments. So this is the direct imaging camera. This part here is the spectrograph. This is the camera of the spectrograph where you can obtain spectra. And this instrument down here is what we are going to use all this night. It's a polarimeter, so it measures polarization of light. And this particular one is called RoboPol. So I will show you a bit more detail later about this device. Inside here, I will not open now, not to spend time. There is a mirror, like a flat mirror that you can rotate. So it diverts the light coming from the mirror to one of these 3 instruments. So within a few minutes, you can rotate this mirror wherever you want, and you can use the instrument that you need for this particular night. So here we can measure 3 main properties of the light. We can measure the total flux in broadbands, different filters using the direct imaging camera, or we can obtain spectra, obtain the spectral lines, their width, measure redshifts and different stuff like that. Now the dome is rotating by itself, so because the telescope is following the sky, and the dome follows the telescope. So now it rotated a little bit. Yeah, and the third instrument gives you polarizations. We measure 3. Basically, we employ here all the possible techniques that are used nowadays in astrophysics. Okay, so I think I will go downstairs. If you have any questions, you can ask me. You can interrupt me. Don't hesitate. Okay, so usually we spend nights in this control room. There is this big and old computer called TCS, the telescope control system. It has this very nice vintage interface, the green numbers on the black background. So here you can see all the numbers related to telescope position and all devices related to the telescope itself. And the camera is controlled through this computer. Here you can obtain shots, change filters, and focus, and do different things like that. But for now, I will not show you how it's observing, but I will show you the images from this polarimeter. Okay, I switch to my computer. Let me start sharing my screen. Okay, can you see my screen?
Yeah.
Okay. So here on the left, you can see this one of the images from this polarimeter, and it looks kind of weird if you only had some experience with direct imaging. So you see that every object here, every star is quadrupled, and there is also this weird shadow here. So the shadow is created by this mask that you can see here or here. So this is the RoboPol polarimeter that I showed you, but from top. This is the entrance, the front lens, where the light from collected by the telescope enters the polarimeter. And in front of this front lens, there is this little mask. It used to be like this of cross shape, but now we replace it by a simpler one with a circle. So this shadow that you see on the image is actually a projection of this mask. Now, inside this polarimeter, it looks like this. So this is the optical scheme of this device. So basically you can say that it's made of three main parts: the collimator here, a bunch of lenses that collimate the incoming light, the polarizing assembly that I will tell you a bit more later, and the camera that focuses light on the CCD detector. And there is also a filter wheel here, so you can observe light in different band passes, in different wavelengths. So this polarizing assembly is made of a combination of a half-wave plates and Wollaston prisms, like shown here. So it's a tricky combination of special crystals. The main job of these crystals is to separate light with different polarization states in separate rays. So these crystals, they have a peculiar property called birefringence. So shortly speaking, this means that light with different polarization has different refractive index in this crystal. So basically, when you put an array of light that has different polarizations through this crystal, it splits into two rays with perpendicular polarization. And this combination of these retarders, half-wave plates, and Wollaston prisms, it splits every image in the sky into 4 images with different polarization states. So every star is split into 4 spots on the CCD, and each of these 4 spots, it has perpendicular polarization. And now you may ask, what is polarization? So I guess you all know that light is an electromagnetic wave, like it's shown here. So it can be described by, maybe not all of you have studied this at school yet, but I guess by the end of the school, you more or less will have an image of this. So this electromagnetic wave can be described by some equations, Maxwell equations, that basically presented as 2 quantities, electric vector and magnetic vector. And each individual electromagnetic wave has oscillations of these 2 vectors, and the plane of oscillation of the electric vector is called the polarization plane. I don't know how much it's clear. So basically there is this animation here. We forget about the electric vector because it's uniquely described by, we forget about the magnetic vector because the electromagnetic wave can be described also by only by electric vector. So in this animation, we show how the electric vector oscillates with time when you have one monochromatic wave propagating in this direction. So the natural light or light from most of the stars, when you look at it with some finite exposure time, like in this particular CCD that we have here, the minimal exposure time is 0.1 second. So during this 0.1 second, even during this short time, there are many, many waves like this passing through the falling on the detector. And all these waves, we have different planes of oscillations of this electric vector. So a normal unpolarized light, if you make a snapshot, I know, 0.1 second exposure, and if you were able to record these planes of oscillations of the electric vector, you would see that we fall sort of directions like shown here. These are this little diagram here shows the projection of a E vector recorded in the plane of a detector. But in some situations, due to different mechanisms, light can be polarized. Then in this case, there is some sort of preference so more of oscillation of electric vector as shown here. And that is 100% polarized. Then there is only one very clear oscillation of a E vector. You can study this during your I hope it will be more clear. So what we do here at the Skinakas Observatory is we measure what fraction of light is polarized and what is the polarization plane. So what is this preferred direction of E vector oscillations when we observe different sort of objects? Stars, active galaxies, asteroids, supernovae, and all sort of astrophysical sources. So this instrument, RoboPol, its main purpose is to find these two parameters, fractional polarization or polarization.
Can you hear us, Manolis?
Okay.
There is noise from you. Okay. Okay.
What kind of noise?
Manolis, could you turn off the microphone? Thank you. Dmitry, we cannot hear you if speak right now. Personally, I cannot hear you.
Μας ακούτε, παιδιά? Όλα εντάξει, μπορούμε να συνεχίσουμε.
Εσάς σας ακούμε, το Δημήτρη.
Ναι.
Dmitry?
Can you hear me now?
Yeah. Okay.
Okay, I assume that you can hear me. If not, signal, make some noise. Okay, so what we do here, we have here the special control system that I can probably show you in my camera. So it's just a special software. You just load targets. You press the button go, and it goes to this particular target that you want in the sky. It's usually a star or an AGN. Then the telescope automatically identifies, makes a shot first of all of the sky, identifies the stars. It uses this service or library called astrometry.net. You can find it online, and it identifies any set of stars that you provided. You can just upload a photo there, and it will tell you, okay, this star is that star. This is another star. It gives you coordinates and everything. So our control system uses this astrometry solution. So despite all these stars are here quadrupled, it still understands, okay, this star is has this particular coordinate, right? Ascension and declination, right? And then it makes pointing correction. So usually first pointing is a little bit off. So our star of interest can be somewhere here. After this astrometric solution, the control system puts it in the central mask. So this mask is needed to reduce the sky background. So as I explained you, everything here is quadrupled. So in every pixel on the CCD, you have 4 rays, also 4 rays from the sky. But introducing this mask, you filter out three out of 4 rays. So you reduce the sky background. And in this case, your measurements of the source that you put in this mask, they are more accurate because you have less noise and higher signal to noise. Okay, so that's why we point our target of interest inside of this little mask. And then there is zoom in of this mask. Our goal is to measure the number of photons in these 4 rays formed on the CCD. As I told you before, we have different polarization states. So here polarization is vertical, here is horizontal, here is by 45 degrees, and here is by 135 degrees. So you measure number of photons using so-called aperture photometry. I will not go into details. You can Google this term. It's a simple idea. Basically, you just count number of photons that fell on the CCD within some circle around your target, and then subtract the background around. And by doing this, and doing this simple math shown here, that is not that important for the moment, you can define these 2 important parameters that I mentioned before, the polarization degree and the polarization angle. It's also called electric vector position angle or polarization plane position angle. So there are different names for this. So basically you have 2 quantities characterizing the polarization of your star or of your blazar, AGN, or any other source. And after this, you can repeat these measurements, for example, and make a time series. So multiple measurements along many nights, and can monitor the same source for several years. And then you can see if this source is variable, you can start analyzing what's happening, why there is this variability polarization. And this is what we have been doing here using this instrument for multiple years, for many years. We were mostly interested in studying active galactic nuclei. So active galactic nuclei is sort of peculiar centers of galaxies. So nowadays we think that basically every galaxy has a supermassive black hole in its center. In some cases, there is a lot of material around this black hole that starts accreting onto this supermassive black hole. It cannot all fall inside the black hole, so it's ejected through due to complicated processes that we do not fully understand. But this material starts being spitted away in 2 directions, in 2 perpendicular directions to the plane of accretion disk. And the speed of this material is very high. It's very close to the speed of light. And sometimes, by chance, these relativistic jets, as we call them, they are pointing towards our line of sight. And due to relativistic effects, they look at this moment very bright because the emission is boosted, relativistically boosted. So there are many unsolved problems related to this sort of objects. And we were trying to observe these sources in polarization. Why they are polarized? Because there is a relatively strong magnetic field in these relativistic jets. And the emission is formed through the so-called synchrotron process. It's when you have a magnetic field line and there is a charged particle, for example, an electron, that propagates along this line, but it starts gyrating, circulating around this magnetic field line. And since it's a charged particle that has an acceleration, it starts emitting photons. And since it's ultra-relativistic, this process is called synchrotron. And by default, this emission that it is produced in this process is very highly polarized. In the ideal situation, it can be 70% polarized. So pretty much this kind of situation when very large fraction of light has a peculiar defined plane where the electric vector oscillates. So we were monitoring these kind of sources, in particular blazars. This is the active galaxies where the jet points towards us. So they are relatively bright and they are very active. I mean, we see the variability with time. And we were measuring polarization of these kind of sources here for several years. And in particular, we were interested in this kind of events that is shown here for one of the blazars with some phone number name. This is so-called electric vector position angle rotation, EVPA rotation or polarization plane rotation. So when you see that this preferred polarization plane, as I was describing you before, with time smoothly rotates in one direction. So you measure today it's like that, you measure tomorrow it's like that, next day it's like that. So it makes full circles and sometimes 2 circles around. And if you plot this position angle as a function of time, GD is the Julian day, which is basically just a day number, you see these rotations as a smooth change of the position angle of a polarization plane. And it was completely unknown some years ago why these events happen in blazars, why this polarization plane rotates. And with this particular instrument and this work done at the Skinakas Observatory, we managed to clarify, to understand this process, to discover why this happens and some to clarify some details related to this. So, for example, we found that basically the how to explain it briefly, the relative velocity of this jet, of this material going towards you in this jet, is related to the amplitude of these events, so how long it was rotating in degrees. We found that luminosity of these sources is related again to the amplitude of these events. We found that these events mostly happen in a particular type of blazars. And many other things like that. So we managed to constrain the hypothesis explaining these sort of events, because there were many explanations how this can be done, how these events could be produced in these sources, but it wasn't clear which exactly of these models is implemented in reality. And later we actually found this particular, very specific behavior of gamma ray photon fluxes in the sources related to this kind of rotations that are shown here in the pink regions. So I will not go into detail because we don't have much time, but basically we found that the model explaining these rotations, and there is no way that any other model can explain this. So the explanation behind this event is that you have a jet with a more or less steady flux, like shown in this picture or in this video. Sorry. I will show you the video. So you have sort of steady jet, but once in a while through the jet, we see propagating so-called blobs of plasma. So condensation sort of clouds, more condensed clouds of plasma. And these clouds of plasma, they cause these kind of polarization plane rotations because they pass through the magnetic field that is helically, that is kind of spiraled in the jet. So it highlights different parts of this magnetic field. And at this particular moment, you see some peculiar orientation of the magnetic field. But since it propagates through the spiral, the magnetic field direction changes. So the polarization plane direction changes. So I see we are running out of time. So I very briefly will tell you that aside from the studying of these jets and active galactic nuclei, we also study the distribution of dust and how the magnetic field is oriented within our galaxy. So there is this tricky mechanism that orients dust particles according to the magnetic field direction in our galaxy. So if you measure stars located behind clouds of dust, you can measure how the magnetic field is oriented within these clouds. And then you can learn how this magnetic field forms these clouds, how it compresses them and study star formation and things like that. Yeah, this one I will skip. So we'll go to the end of my presentation, which is longer than I expected. So we have been running RoboPol. Here I give you some reference where you can find our works. We published a number of works in many different fields studying this polarization. But now we're switching to a new generation of instrumentation. We are now building these two polarimeters that is like a successor of RoboPol. It will be wide field polarimeters. So we'll, instead of one target measured in this mask, we will measure all targets in the field, and the field will be 30 by 30 arcminutes, so it's very large. We'll be measuring hundreds of stars in one exposure. So we will build two of such polarimeters. One will go here at the telescope that I was showing you in the beginning, and another one will go in the South African Astrophysical Observatory. So we will be able to monitor both northern sky and the southern sky. And our goal is to measure millions of stars in polarization close to the galactic plane poles. And doing this and studying polarization of the dust, dust-induced polarization of stars, we will be able to measure the magnetic field in our galaxy and make what we call 3D tomography of the magnetic field in our galaxy. And this will be used for several different purposes. So you can study the dust by itself, how it forms, what is made of, how it affects the formation of dense clouds, the star formation and stuff like that, how the magnetic field intervene in this process. And on the other hand, it will be very useful for experiments that try to measure polarization of microwave background. So it's a different band, it's millimeter waves that you cannot see by eye. It's a radio telescope basically that measure that stuff. And that will give us some clues about the very early moments of the universe. Because polarization there, it's very important. It can constrain models, again, how inflation was acting at the very early moments of existence of our universe. So yeah, you can make a screenshot of this page and follow our webpage, which is shown here, robopolphysics.eoc.gr. There are some photos and some publications there. Yeah, and probably there you can find also my contacts if you have some questions or some comments. Go ahead, send us a message, or you can ask me anything now. Sorry, it was a bit messy. I hope you got something. Yeah, thank you.
Thank you, Dmitry, so much. Think about that in this field, the Skinakas Observatory is really in the state of the art. This is the key.
Yes, this polarimeter, it's
Thank you very much, Dmitry. Thank you very much, Panagiotis.
You're welcome.